Hello everybody. In the last few classes we are looking at minimization of circuit, a logic circuit, and different methods, different ways, and in the last class also we defined certain cost, and we were looking for getting a lower cost in terms of hardware that is being used for realization. In this particular class we shall look at some of the practical issues associated with logic circuit implementation, and for that how we modify the circuit, which may be more costly in terms of the hardware used, the way we have defined cost, but it saves the day. It helps in overcoming some of the inherent problems associated with the logic circuit. And the concepts are to be covered, which is related to propagation delay and the glitch that is formed, and we shall dwell on static one hazard in today's class. So, we look at again a very simple problem, the kind of problem we have seen before. So, this is a minimization of a truth table using Karnaugh map, where there are 4 minterms present, and this for this minterm, this one and this one are covered by A prime C, this one and this one are covered by A B. Okay. And there is another way we can have this one and this one covered by B C, right, but these 2 ones are already covered by A B and A prime C. So, A B and A prime C are essential prime implicants, essential because they are covering either this one or the other one, which is not covered by anyone else, and in this case B C becomes non-essential. So, it is redundant. Okay. So, the circuit for the equation that we get for this truth table for minimized expression is A prime C plus A B, and this is how you realize the circuit. Okay. We could have obtained, we could have had a B C also associated with no difference in meaning, but that would have unnecessarily increased the hardware cost, okay, because B C means another AND gate and that will get connected. Okay. So, this is how we have seen the minimization problem so far and circuit realization, and in doing this what we have considered that the we did not consider the effect of propagation delay in the logic gates. Okay. This was not considered, we just went by the Boolean expression what will give us the minimized circuit. Okay. So, this is the background for with which we start today's class. But we noted before that there is propagation delay in a particular logic gate, whatever logic gate we talk about. Okay. So, this propagation delay is associated with for example, now we are looking at it in terms of voltage that is presented. Okay. So, earlier we are writing say 0 on 1 0 and all, which is fine, but if you look at input voltage and the output voltage. So, if you are stretching it in time and all, actually you will see that it is not very sharp kind of rise. So, there is a kind of finite rise time and finite fall time. So, in the input side the time the 50% of when it reaches the 50% level as the inverter, and corresponding output that falls, output will go down, go low, right, when it reaches the 50% value. This is the propagation delay which is at the output, which is high to low. Okay. This is propagation delay at the output for output going high to low, and similarly the opposite is low to high, that is input is at 50% level when it is going from high to low, from that output is going from low to high when it reaches the 50% level. So, this is propagation delay at the output low to high. Okay. So, this is because of usually they will be a little bit different from one another, because if you look at the CMOS, there is a capacitance we had noted before, load capacitance, right. So, this charging path, so this is the charging path and discharging path is like this, right. So, these paths are different. Similarly, in this case this is one path and this is another path, right. So, there is a small difference between these two values, okay, but average propagation delay is taken is the you add them up and then divide by 2, okay, and for TTL it is of the order of 10 nanosecond. CMOS for same 5 voltage circuits like that of TTL it is of the order of 50 nanosecond, but it depends on load, and also for CMOS if you increase the voltage level say to say 10 volt instead of 5 volt, it will become say 30 nanosecond of that order, okay. But there is a finite propagation delay which is to be noted in this particular discussion, okay. Now what is its effect? Because of this what happens? Because of this we will find in the circuit there may be glitches, okay, and so we will see how it occurs, but before that let us define what is glitch. Glitches are undesired positive or negative going pulses. Undesired means this is positive going pulses and this is negative going pulses. Undesired means it was not supposed to go. So, it was supposed to be straight like this, right, but then there is some such thing happening, and glitch occurs due to finite propagation delay of logic gates and occurs for specific combination of input. So, for certain specific combination of input only it will happen, it is not occurring all the time. For another combination it will not, it may not occur, okay. And glitch is transient in nature, it is there and for a very short duration of the order of the propagation delay. So, if something in the input is getting changed, so momentarily it will occur and then it will disappear. In the stable state it will not be there, okay. And the other definition which we need to take note of is called hazard. A logic circuit has hazard if there is a potential for glitch. So, a circuit which is hazard free, there is no such potential, okay. There is no such combination at the input, some changes for which glitch will occur. So, that is a completely hazard free circuit, okay. And a circuit with hazard may generate glitch if those specific input condition or the pattern is presented, okay. So, this is we take note of, right, and then we shall look into examples. So, we go back to our this previous circuit only, the circuit with which we started. This is the one, okay, and this was the our reduced circuit, reduced relationship optimized from K-map, right, and this is the corresponding circuit. Now, we consider a specific case, say B is equal to 1, C is equal to 1, okay. So, at that time what will happen? What is the value of the output? B is equal to 1 and C is equal to 1. Right. So, in the truth table, in the truth table if you look at it, you will find that the B is equal to 1, C is equal to 1 is 1, okay, and it is obtained from the equation also. If you just substitute it here, so A prime 1, 1, A prime, right. So, this is the cases. So, you get A prime plus A and this is 1. So, that means y will always be 1 as per the Boolean algebra, right. So, this is the case. Now, you consider that B is at 1. So, this is at 1, C is at 1, right, and A goes from 1 to 0. So, A goes from 1 to 0, right. So, when A was 1 in the stable condition before this change takes place, so this NOT gate output was 0, right. Now, when A goes from 1 to 0, so immediately this input is becoming 0 at that time point, but this NOT gate output will not go to 0, will not go to 1 immediately because of the propagation delay just now we had considered in the previous slide. So, it will go to 1 after some time, right. So, for that amount of period, for which this NOT gate output goes from logic low to high, okay. So, till that particular time, that particular delay output, propagation delay low to high, at that time this remains at 0. So, this AND gate output as a 0, after of course, the propagation delay it will get the 0, and this is already in 0, right. So, what we see that OR gate both the outputs are 0, even for small duration, after that it will become 1. So, for that small duration, after again its own propagation delay, the OR gate will generate a 0 which was otherwise 1. Okay. So, that is the after that propagation delay, of course, it becomes 1, and then there is no issue. One of the OR gate input is 1 except for that transition period. Is it clear? So, this is the case when it is happening, when you see that a glitch is occurring for this OR gate output is momentarily going to low. Okay. But if B is equal to 1, C is equal to 1 and A goes from 0 to 1, will there be any issue? Will there be any glitch? So, this is 0. So, this is 0, right, and this is 1 means this is 0 means this was already in 1, then change takes place. So, this 0 becomes 1, right, immediately, but this 1 is held, 1 will go to 0 after the propagation delay, right. But by that time this AND gate output both of them are 1. So, this is 1. So, OR gate will be held at 1, there is no issue. So, that is what is known, that is what was talked about as the specific input combination, only the glitch will occur. This circuit is having a hazard. Okay, this is not a hazard free circuit, because there is a potential glitch, but glitch will occur only when a specific combination is presented. Okay. Now, we define static 1 hazard. What is it? Static 1 hazard is the case when output should remain, output is to remain at static 1, static at 1, okay, according to Boolean logic or algebra, the expression, but glitch occurs under certain condition. So, essentially what we had seen that somehow the circuit boils down to a condition which is after considering all the different inputs, the values of those inputs, an expression something like this. Okay. So, that gives rise to the static 1 hazard. Okay. If somehow this kind of expression is there, and the corresponding realization, if you look at it, if you are having it in terms of circuit based realization. So, this is the essence of it. Finally, it boils down to a reduced circuit like this. Okay. There may be additional gates and all. So, those delays will be considered, but this is the basis of the static 1 hazard that is occurring. Okay. So, how again whatever we just mentioned, if we try to put it in the form of diagram for this particular circuit. So, this is A, right, going from 1 to 0 over here at this time point, okay. And because of this A bar will go high after the corresponding delay, propagation delay logic low to high, right. So, from this point to this point there is a delay, right, and momentarily you see at this point of time this and this both are low. Okay. So, because of which OR gate output after its own propagation delay, which is high to low, right, given by tau 2 over here. Okay. So, it will go to low because both of them are low at this point. So, this is going to low. Okay. So, tau 1 and tau 2 could be different, but as I said, in the same logic family we usually take them as same tau, and the low to high and high to low also can be different, but more or less for this depiction we can show them as same. And after that this propagation delay, this goes to high, this output will go to high, and because of which again our get output will go to 1, right, after its and it will remain low for that period only. Is it clear? Okay. So, this is how the glitch is occurring. Now, how we can detect static 1 hazard? So, is there any rule for that? Okay. So, yes, there is a rule, there is a method by which we can detect static 1 hazard, and later on we shall see if we can cover those hazards, we can make the circuit hazard free. Okay. How we can do that? So, for that we have already noted the Boolean expression finally reduces to produces some a plus a prime kind of thing for certain condition, certain specific condition of the input. The other important thing that we can look at even without going into a optimized expression also, just by looking at the Karnaugh map we can figure out the way we form the groups, whether there is a potential glitch there or not. Okay. So, how we can find it out? So, let us look at this example, a similar example similar to a previous example. Okay. So, these are the two ones and these are the two ones. So, obviously, we are forming a group like this, these two prime implicants. Okay. So, is there a potential hazard? Yes, the rule says if the two logically adjacent cells with output 1 in Karnaugh map is not covered by a common product term. Okay. So, this one and this one are adjacent, they are not covered by one common product term, it is covered by this group is generating one product term, this group is generating another product term, is not it? Okay. So, it is having a potential static 1, I mean it is having a static 1 hazard potential glitch, under certain condition it might occur. So, let us see how it occurs. So, we can write from this y is equal to b prime c, this one is b prime c and this one is a b, right, this group is a b and this is b prime c, right. Now, when a c is equal to 1 1, a and c are 1 1, we get y is b plus b prime. This is a case of static 1 hazard, the kind of thing that we have seen. So, if the input is 1 1 1 and then from that it goes to 1 0 1, okay, that means b goes from 1 to 0, the way we have seen before, then a glitch, a negative going pulse will be there. Okay. So, that is what we see from this particular case, we can identify, right. This is not covered. Okay. Let us look at this example. So, this is an example where there are two such prime implicants b prime c and b c prime. Okay. So, is there any hazard here? So, there is no logically adjacent cells which is not having a common term. So, these two are logically adjacent, a common product term, these two are logically adjacent, common product term. Okay. And these two are not logically adjacent, say this one not logically adjacent. So, they are need not be covered. Okay. So, there is no such common term is required. So, this is not having any hazard, okay, because we are in all these cases we are considering only one variable changing, right. And so, if you see that if you consider say b is equal to 0, right, then this term will not be there, it is only b prime c. So, it will follow if c changes with appropriate propagation delay, output will change accordingly. Okay. So, there is no such hazard. So, these were 3 variable examples, we look at a 4 variable example. So, this is the corresponding Karnaugh map of a given truth table. Okay. So, the way we optimize get a optimized expression for this circuit is a group of 4 over here and a group of 2, right. So, this is generating you a BC, right, this is generating BC and this is generating a C prime D prime, this term, right. Okay. So, you just OR them and you get the minimized SOP realization. Does it have a static one hazard? Let us look at if there is a logically adjacent ones. So, this one, and this one, they are logically adjacent, which are not having a common product term, right. So, there is a potential static one hazard. And when does it occur? For which combination? So, it occurs, this is the thing. So, A, B, D. So, we can see that A, B, 1, 1, and between these two, what is common? D with 0. So, A, B, D, 1, 1, 0. So, this is common between these two ones, right. And C going from 1 to 0, C going from 1 to 0, because we know that from high to low, then there is a a static one hazard. So, in that case, A, B, D remaining, A and B remaining at 1 and D remaining at 0, these are the cases, and C going from 1 to 0, we are having a glitch, okay. And also from Boolean expression also you can find it out, right. So, this is just examining that whether this rule prevails or not, and we can find out the condition also by this when the glitch will occur, and so this is how we can detect static one hazard. But knowing that there is a static one hazard, that is not enough. We need to see that we are able to cover it. Okay. We are able to cover it, and the circuit does not have hazard, because those negative going pulse or positive going pulse, I mean in this case negative going pulse for static one hazard might cause some trigger certain events which is undesirable. Okay. So, in the example that we had taken before, right. So, since it is caused by the I mean during the detection process we have seen that it is caused by the logically adjacent terms not coming under one one common product term, okay. That is the cause of it. So, the solution is to have a common product term that covers logically adjacent ones in the output of a function in a Karnaugh map, okay. So, that is the solution. So, in this case the example that we started with, right. So, this is this one and this one did not have the logically have a one common product term. So, now we look at one common product term that can be there. So, this common product term is nothing but your BC, okay, which we saw there in the first place, but we abandoned it because of higher cost that was getting associated with it. I mean when you include it, that is a redundant term, right. But in this case when you associate it, okay, the hazard gets covered and we can get a hazard free circuit, okay. So, this B and C, this was the earlier circuit, now this B and C is coming over here, and how is it helping? So, B and C 1 1, then only the hazard I mean the glitch was there, right. So, B and C 1 and 1, what is happening? This is 1, this is 1. So, the output is held at 1, you or get any output is 1, is output is 1, right. So, even if A changes from 1 to 0 and there are some changes happening over here, some changes happening here, momentarily they are becoming 0, this is becoming 0 for some time, this is becoming 0 for some time, okay. So, 1 to 0, A 1 to 0, so this has become 0, it is still 0, right. It is taking some time to go to 1. So, this is the time we are talking about when both the outputs are 0, right. It is taking some time to go to 1, okay. But these two zeros, even if it is there, this 1 over here is suppressing the glitch that could have had been placed unless could have been there had this output is not there. Okay, this additional circuit. Okay, so yes, it is more costly, but it is removing the hazard. Okay, more costly in terms of hardware cost, but it saves some other cost in terms of performance, where these glitches are can cause damage. Okay, so this is the thing that we have to keep in our mind. Finally, we look at the other example we had discussed before. So this was the circuit, and these were the two terms. This was one term, and this is another term, BC and A C prime D prime, right? And this is the so-called redundant term, right? But this generates a product term which connects, which is common across logically adjacent ones, okay, which is otherwise would not be connected. So that is the A B D prime, and this A B D prime, if you remember, that was the condition at the input side when A is 1, B is 1 and D is equal to 0, and C was changing from 1 to 0, the glitch was occurring. Okay. So by having these 3 and the cases, I mean A, B, D prime connected here, for this particular cases when the glitch could have been there, putting such additional 3 input AND gate and connecting to a OR gate, right, you are suppressing that glitch. Okay. So this is what we keep in mind, and also we take note of that it is not that the circuit may have only one hazard, there can be multiple hazard also, I mean multiple such possible cases, right. For example, if in this particular example, if we just simply modify, like this is 1 and say this is 1, right, then minimized representation will be like this, this one and the other one. Now to make it hazard free, so there are now two potential, if you look at it, there are two such potential glitches. Okay, one is this is the one that we have already seen, another is this particular case. Okay, these two are logically adjacent but not covered by any common term, common product term in the most minimized case. So to cover this, we need to generate this term and add it here. Okay, for that particular minimized expression. So this is we take note of, and with this we summarize what we discussed today, that logic circuit minimization on its own does not consider the effect of propagation delay. Glitches are undesired short duration pulse that may occur in a transition due to finite propagation delay for certain input combination. A circuit with a potential for glitch is considered to have hazard. In static 1 hazard, output should remain at static 1, but glitch may occur for that specific combination. Static 1 hazard can be detected by examining the K-map or the Boolean expression. K-map comes first, so we can look at the K-map, and from that we can look at these logically adjacent ones. All logically adjacent ones are covered by one common product term or not, and circuit can be made hazard free by covering hazards by additional terms which are otherwise considered redundant. Okay, thank you.